Hello, welcome back to Cracking the Cryptic, and a complete prison of a puzzle today. I'm looking forward to having a go at that. I want to say thank you, first of all, to the many people who have commiserated very generously with me about my appearance in the Countdown quarterfinals, which was brief in the sense that I only got through one game. Well, I didn't get through it. I lost my quarterfinal. Congratulations to Jessica Pratesi, who you may already have had the chance to see today playing in her own semi-final. I'm not going to spoiler the result in case you haven't watched that yet, but I do think it was possibly the best game of the series to date. So, well worth a watch if you have the opportunity and you haven't seen that. Absolutely fascinating. Now, I got to see it during the filming process, so that's why I have seen it before it's actually come out, which is when I'm recording this video. Now, Tomato Pie has sent us a puzzle today, and it's a debut, and I'm looking forward to giving it a go. Now, I've forgotten the reason it's called non-ship or Dutch. Well, I know about the Dutch. Anyway, double Dutch it's based on, isn't it? Right, okay, yes it is. That's fair enough. Now, there are other things, of course, that we like to mention, like coming up on the 1st of July, a new Sudoku hunt. And we're really looking forward to bringing you a debut hunt by pause. Definitely easier. The easiest of the year. The most approachable. There are puzzles there that are not easy, but if you see the way, they can all be done. And we urge you to have a go. It's going to be good fun. Now, there's plenty of other things around the channel. There's all our apps, which are fantastic. There is Sven's Sudoku pad and our merch, and they're all on the links under the video. Our apps do include Line Sudoku, that's our latest so far, and Arrow Sudoku, so relevance to today's puzzle. But I'm going to go through the rules now of today's puzzle, and we will see how we get on with it. So normal Sudoku rules apply. Numbers 1 to 9 in every row, every column, and every box. Adjacent digits along an orange line must have a difference of at least 4. So you could put 1 and 5 in these cells, or 1 and 8, but not 3 and 6 in these two neighbouring cells. I did recolor Tomato Pie's lines from yellow to orange because we're kind of familiar with orange as the number for a Dutch whisper line, as the colour for a Dutch whisper line, as it's called. Now, each number in the grid indicates the height of a skyscraper in its cell. You have to imagine this grid as a block of city skyscrapers. And a clue outside the grid, like this 3, indicates the number of skyscrapers visible from that direction, where taller skyscrapers block shorter ones from view. So this row could begin from this end, 1, 5, 9, for instance. From the other end, we're looking at the other view, so maybe it would go 7 there, then there'd be an 8 here, and then the 9 that we mentioned there. And they would be the only visible skyscrapers, hence 3 of them. And that's why the clue would be 3. It's a slightly complicated rule if you haven't played it before, but once you get used to it, I don't find it easy to use, but I do understand it. Now, digits on an arrow, sum to the digit in that arrow's circle, so those two add up to that one. And an inequality symbol between 2 digits sort of points to the smaller digit. These just act like greater than, less than signs. This digit must be greater than that one. A digit in a grey square is even. Now, there is a little PS on the rules that the lines also fulfill the constraints of 2 other types of lines in variant Sudoku, and you get bonus points from Tomato Pie if you know what they are. It's a fascinating thing. That isn't clearly not relevant to solving the puzzle. Well, you never know, but it's certainly not a rule. It's just a PS. So do give it a try on the link under the video. I am going to start now, and I'm going to say, let's get cracking. And we're going to see. These skyscraper, arrow, and inequality clues are very minimalistic. There's really not a lot of them. And even, I mean, in the top row, greater than 1, all that's telling me is that 9's not at either end, I think. So what I'm going to do, basically, is discount the value of those clues. I'm going to have to think about the orange lines. Now, what we have come across before, it's quite a long time, although we occasionally get echoes of it, is that there is only one way to connect all 9 digits with these Dutch whisper relationships in a circle, in a repeating 9-digit series. And I'm going to have to work out what that is. Now, I think that is going to have to be relevant for solving this puzzle. Even though a 9-digit series that does not connect to itself is not quite the same thing as that. And I think part of the puzzle is going to be to A, establish that 9-digit series, B, establish why every row conforms to it, because I suspect every row will, and then C, work out how to use the outside clues to disambiguate which row is which. That's my imagination of what we've got to do. So I'm going to establish the 9-digit series first of all, I'm going to do it in this row just randomly chosen, and you have to assume that it's toroidal, so that that cell connects to that cell with an orange line. Now, wherever 5 appears, the only digits that can be next to it are 1 and 9. So let's just randomly choose a place to put 5 in, with 1 and 9 either side. Then you have to consider the digit 4. 4 has only 2 possible neighbours, and they are 8 and 9. And therefore, wherever 4 appeared on a repeating line, it would have to be between 9 and 8. And you can do the same thing for 6, whose only 2 neighbours are 1 and 2. So 6 has to be next to 1, and remember that's at the other end of the line. And then the 2 digits we have to fit in are 7 and 3, and they work very well. They fit in there and there. I think you'll see that every pair of digits on this never-ending sequence has a difference of 4 or 5. But that is the sequence of digits. Now, why do I believe that none of these are going to use a different sequence of digits? It's partly because I can imagine using this and then using the same sequence. I mean, I suppose if you put it in here, 1, 5, 9, 4, 8, 3, 7, 2, 6, you'd ensure no clashes. And then if you put it in here, 1, 5, 9, 4, 8, 3, 7, 2, 6, you'd ensure no vertical clashes again. And you've also ensured no box clashes by the spacing. I just can visualize that you could fill the grid like that. So that's part of the reason I think it will be used. Now, that is not the same as establishing that no other version can be used, because determining the order of these digits entirely depended on a belief that they would all reconnect up in one cycle. So it is still true for a number of these digits that they only have a few possible neighbours, 2 possible neighbours. And that is the case for 1, for 6, for 4, and for not for 1. It's not the case for 1. 1 could neighbour 5, 6, 7, 8, or 9. Not 1, but 5, 4, and 6. They can only have 2 possible neighbours. So you could theoretically start a line not with 6. Sorry, if you started a line with 6, it wouldn't have to have 2 next, is what I mean. It could be next to a 1. So maybe in theory you could have... Oh, sorry, that's not what I was trying to do. I'm in the wrong mode. Maybe in theory you could have a line that started 6, 1, and then did the other thing, 5, 9, 4, 8, 3, 7, 2. And you could. So I'm going to have to come up with a reason that that doesn't happen. And I don't know what that is immediately. So I'm going to have to ponder this. This is, I mean, I'm sure... Oh, sorry, I just lost the screen there. I'm sure that that there is a reason why we're going to have to reuse and reuse this sequence, either forwards or backwards. It may not make any difference which. So I'm going to just have to ponder that a bit further. Yeah, okay. Here's what I'm going to allege. That the scheme I was beginning to sketch out earlier, where you use this sequence and you start it here in row 7, say, and you start it here in row 1, and you wrap around to the beginning of the grid, that will allow complete filling of the grid with the same sequence in the same order, just run round, because obviously you can set it up so that every column, so that the one starts in a different column every time, and therefore every column will obey Sudoku rules. How can you make sure that every box will obey Sudoku rules? Well, this is one way, where if you start with the 1 here in row 7, and then have 5, 9, 4, 8, 3, 7, 2, and start with 6 at the beginning, and 1 here, then that will, I think, make sure that as long as you have one of these beginning 4, 8, 3, and one of them beginning 7, 2, 6, the same thing will apply throughout, and all the boxes will work. So what I'm proving there is the positive possibility that this can work this way. I think the negative possibility that it can't work any other way is proved by the fact that if you consider starting with 6, 1 from this end, I mean, I just demonstrated that there is a disposition of digits that obeys that for the row, that obeys the rule for the line in the row. That does. But the problem you then run into is if you try and replicate that row in every row, column, or box, at some point now, oh, actually, all I've done here is reverse that. So this is just one of the subsets of the digits I'm talking about. Oh, that's quite interesting. Right, now I'm understanding a bit better. No, let me put that back in. Right, and try and explain what I'm talking about. So I did say a moment ago that either we're going to put this sequence in one row and cycle it in every other row by one offset cell. And it's either that or the reverse of this digit, of this string, which would be 627384951. And what this row is in fact that reversal, starting here and continuing from here, 627384951. And this was the only other way, I think, of beginning with a 6. So 1's only neighbours are... No, 1 has other neighbours. Let me just see whether you could begin 6, 1 and then achieve something else. So the point there is that 5 is going to have to appear somewhere, and its only possible neighbours can be 1 and 9. So if you put it here, you're doing this whole reversal. But you could theoretically in this row have 5 and 9 at that end. Now, the reason that's not going to work is that 4 has to have 9 and 8 as neighbours. Then you have to fit 3, 7 and 2 in. And this is going to end up being 2 or 3, so that you can keep 7 away from... Well, either this is going to end up being 2 or 3, or if it's 7, that's a 2-3 pair. And it just won't work any other way. So I think it's sort of a proof by example, but I think this is exhaustive. And I challenge you to tell me otherwise. I think that we have shown that we need to use either this sequence or its reversal and then cycle it in every row. And I'm going to do that. Oh, okay, what I shouldn't have done there is delete it. So I can delete the colours. But I do want to know what this sequence is. And now I'm leaving that in as an aide-memoire. Let's colour it all yellow. Yellow is the aide-memoire row. because I want to start in the skyscraper rows where I think there is more information, because there are at least 6 clues here rather than just one arrow or that little sequence of information. So I'm going to start up here. And the 3 is the 2 the most specific? Let's look at the 3. Yeah, basically we could just look at every version of this sequence and see when it yields 3 from either end as the skyscraper clues. And this sequence doesn't. It is 3 from the left, interestingly, 1, 5, 9. But from the right, the buildings you would see are 6, 7, 8, 9, which would give you a 4 clue. So that's not right. So if we started instead the row with 5, we'd only have 2 from the left. If we started with 9, we'd only have 1 from the left. However, if we start from 4, we go 4, 8, and then we see 9. That's no good, because from the other end we'd start with 9 and we'd only see 1. Oh, this is going to really throw me if there isn't a valid row. 8. No, if we start from 8, we'll only see 2 from the left. If we start from 3 on the left, then we'll see 3, 7, 9. And from the right, well, then we'll see 8, 9, and that's only 2. And now I'm beginning to think there isn't going to be a valid sequence. Starting from 7 will only give 2 from the left. Starting from 2, 2, 6, 1, 5, 9. Yes, that's the one. So I'm going to write it in here as another aide-memoire for a very specific reason. I'm not just filling this into row. Sorry, let me get the order right. So this is a cycle of that row. And this would yield 3 at either end. Now, the reason I'm not just writing that in here is because it could go in either way. If you wrote it in the backwards as 7, 3, 8, 4, 9, 5, 1, 6, 2, that would give you a 3 as the skyscraper clue at both ends as well. You'd be seeing 7, 8, 9 from one end and 2, 6, 9 from the other. So I don't know which way round this goes, but I do know that it's got 9 in the middle, a 5, 4 pair surrounding it, a 1, 8 pair surrounding them, a 3, 6 pair surrounding them, and a 3, 6, and a 2, 7 pair at the ends. And that is how row 2 will be formed. So that was another aide-memoire. We'll get rid of that now. Now, I'm going to try and do the same sort of case testing for row 3, because I don't see how else you can solve this puzzle. I do have the extra clue this time that you can't have 4, 5, or 9 in the central 3 digits. Actually, that's quite useful. So, given that 5, 9, 4 are a trio that come together, well, they've either got to be here, here, or in one of the overlapping positions. Remember, it's a torus. So let's start with 5 here and see what the numbers are. So we go 5, 9, 4, and that is 2 from the right. Oh, that's very plausible, because then we have 8 from the left. So I think it could be 5, 9, 4, either from that position going to the right or from that position going to the left. I wonder if anything else fulfills it though. We have to check. So if you started here, 5, 9, you'd have a 1 from the right. That's no good. If you started here, you'd have a 9 there, and that's 1 from the left. If you start here, 5, 9, 4, that's fine from the left. But then you go 8, 3, 7, 2, 6, 1. And you see loads of buildings from the right, many more than 2. So that's not it. If you start here, you've got, well, it's this row, which is 3 from the left. That's no good. And you can't start here because you're going to push 9 and 4 into the middle. Okay, so we have established that this row will have a 5 in one of those 2 positions. And then it will go 5, 9, 4 going outwards. So 5 in one of those 2 positions, 9 in one of those, 4 in one of those. Then we go to the other end of the line and we have 8, 3, 7, 2, 6 definitely in what is now the middle of the row, and then 1. Now, some of these must rule each other out. This is either going 8, 3, 7, in which case this would have to be 5, 9, 4, or this is going the other way, 8, 3, 7. This would be 1, 6, 2, which actually has no bearing on this at all. Oh, okay, bother. Right, okay, what I'm going to do then, I've got a genuine triple here and a genuine triple here. This is 8, 3, 7, and 3 always comes in the middle of that. So I'm going to put 3 there and 8, 7 here. And now the only rule I've got in this row is that I mustn't have 9 at one end or the other to ensure that I can see at least 2 buildings. So I may not be able to disambiguate this, but 8, 3, 7, if I was to put 2, 6, 1 in this side, that would be 8, 3, 7, and that would be 5, 9, 4. That would work fine. If instead I was reversed and I went 7, 3, 8, this would be 4, 9, 5. I don't know. 2, 6, 7, 8, 3, 7. This would be 2, 6, 1. This would be 5, 9, 4. The rule would be obeyed. It's possible I'm not going to get any more info out of this, which is really quite surprising. Okay, we're either, though, going 8, 3, 7 that way, in which case this goes 2, 6, 1. Oh, sorry, I've mistyped a digit. 2, 6, 1, 5, 9, 4. Or we're going 8, 3, 7 the other way, in which case we go 2, 6, 1, 5, 9, 4. So we've got 2 possibilities for each cell. And annoyingly, I haven't really got very close to understanding how these fit together, and I'm going to have to use the other groups of rows to back into that. Yeah, that's quite surprising to me, and I get this as a definite 3, 9, 6 triple. Remember, this is just aide-memoire. Okay, I'm going to try and come down and use these cells now. So, this time, I don't understand how this is. Oh, this is a very interesting greater than sign, because we're using this cycling sequence, but we have a Dutch whisper here. Oh no, that's fine. Every single one of these differences was 4 or 5, and that's going to fulfill the rule. Oh, bother. Okay, that's not a very interesting greater than sign. Okay, let's look at even digits in this column. Remembering this is just aide-memoire. So that is going to be even. That one might be, and that one won't be. What's this going to be then? This... I suppose what we have to do is consider that the remaining digits in the middle column are going to be 1, 5, 2, 4, 7, and 8. The trouble is I just don't know which way round we're going in this puzzle. It's a strange one. It's a strange one. 6, 1, 5, 9, 4. Okay, so the rows that begin here, it's no coincidence that 3, 9, and 6 are the middles and that they're spaced in this row. That's all to do with how you're going to fit 3 sets of this cycle into boxes. And that's going to mean that one of these groups is 5, 8, and 2, and one of them is 1, 4, and 7. Now, how's that going to pan out in terms of what goes here? Do these alternate? No, the evens are very oddly spaced. I'm wondering about the even cell now. Oh, well, hang on. What can this even cell be? It can't be 2 because it's got 2 digits lower on both ends. So that is 4, 6, or 8. Right. And the digit above and below it are going to have to be spaced 3 apart. I think that's what we've learned up here. Those are spaced 3 apart. We're going to be using the same direction in each row, whether it's forwards or backwards. It's going to be the same direction. And therefore, every group of these 3 cells are going to be spaced 3 apart. For instance, this is either going to be 417 here, 417. They're spaced 3 apart in our original row. 369 there, we know they're spaced 3 apart. And in one of them we're going to have 528. It could be here 528, or it could be here 285. We're always going to use these kind of modulo sets actually in every down trio. That's really interesting. That is a function of what we've learned, what we've done. So this is a modulo set of either 852, 417, or 369. Well, in which of those modulo sets is the highest digit even? It's 852. So this is an 8. Isn't that intriguing? So what I'm doing is using what I've learned about the rest of the puzzle to understand these little vertical trios. And there we go. This is going to deal with it because 8 there makes that a 4. And now we know which way round we're going here. We're going in this sequence order. Like I've done it in the correct order to the right. So we're going 6, 1, 5, 9, 4, 8, 3, 7, 2. Because that 8 turned that into a 4. And there we go. That has, I'm going to get rid of the aide-memoire row. We don't need that anymore. And now I could actually just, well, I'm going to reuse this cycling sequence everywhere. But this is a 417 set because we need these modulo trios in each row. Isn't this a weird puzzle? It's so strange that it works this way, but it does. And it's very clever. 2, 6, 1, 5 there. And then up here, we've got the 1 there. So we go 5, 9, 4. I mean, it's going to be quite easy to fill this in, I imagine. 8, 3, 7, 2, 6. Now down here, we've got an 8 there. So I can fill in the whole row as the same cycle repeating. It's a very unusual puzzle. Now, I think now I do use this because that can't be a 2 because it wouldn't obey the Dutch whisper rule. So that's the 5 and that's the 2. And now as I fill these rows in based on the cycling sequence, the old peloton, in it goes 9, 4, 8, 3, 7, 2, 6, 1. And that obeys the rule there, 1 and 5. So now I have 3, 6, 9 here. Now I just have to find how these 3 rows slot together using this arrow. And we're done suddenly, which is quite strange. So these are the trios. Oh, but modulo arithmetic gives me a lot of ways of this working. This could be 1 plus 2 equals 3 at the absolute minimum. 1 plus 5 equals 6. 4 plus 2 equals 6. 1 plus 8, or 4 plus 5, or 7 plus 2 equals 9. Well, how do I work out? I mean, I could fill in these triples. They're obviously going to repeat these modular sets. But I don't know. Sorry, I have not understood how. It must be something to do with the fact that these need to all be different digits. So 1, 2, 3 would make this 159, 726, 483. Well, that works. 156 would make this. Oh, that doesn't work because 159 would go here. So you'd have 5s in both those cells. 426 would give you 483, 726. That's no good as well, because you'd now repeat 6 in those cells. That was a little harder to falsify, but now we know it's not a 6 here. 3 is possible. I suspect 3 is going to be right, but I'm going to have to prove that 189, 459 and 729 don't work. 1 would be 159. That would break with the 9. 459 would lead to this being 483, this being 159, and that's a repeat of the 5s, so that doesn't work. And 729 would have this being 726 with a 2 there. So, my goodness, the only way this does actually work is 1, 2, 3 on the arrow, the minimal arrow. And now we can just fill in the sequences again, and we must be finished. It's a very interesting puzzle. I mean, it's like a mathematician's dream, but a logician's nightmare in a way. 4, 8, 3, 7. It doesn't, in some ways, it doesn't feel like I've done a sudoku puzzle. It feels like I've done a different sort of mental test today, which perhaps restores my equilibrium after the countdown flop and so on. So there we go. That is the correct solution. I think the logic to prove that we had to recycle that one sequence. Oh, it was in row 6 in the end. At the beginning, either one way or the other. I think that logic was sound, but do leave a comment if you had a different view on that. It's a very interesting idea. I'm wildly confident this is the only correct solution. I'm not 100% confident that I proved it was the only correct solution, so we'll see what you say. I think I did, but I will be interested in your thoughts. Thank you, Tomato Pie. Now, there was an extra PS, wasn't there? The lines also fulfill the constraints of 2 other types of line invariant Sudoku. Bonus points from Tomato Pie if you know what they are. Well, I was assuming, actually, we would have modular and entropic. And now I think about that, that's absolute nonsense. You couldn't fulfill both. But surely we fulfill modular. 4, 9, 5 are all from different modulos. That is the kind of vertical keypad sequences. 9, 5, 1, the same. Yeah, we definitely fulfill modulo rules. 5, 1, 6. We do not fulfill entropic rules because every set of 3 would have to have 1 high, 1 low, and 1 medium digit. And there, for instance, you have 2 high digits. So it's not that. Of course, I think the other line rule that Tomato Pie is talking about is Renban, because obviously they're each a set of the digits from 1 to 9. Now, I mean, that is simplistic and would have been obvious before you started the puzzle. I didn't think about it because I was going to leave that to the end, but there it is. So Renban and modular lines is my claim for the other 2 standard types of line, that those fulfill the rules of. That's quite amusing. I hope I've picked up the bonus points today. We will see you again tomorrow. Thank you for watching, and bye for now.